We are currently discussing probabilistic parsing, and this is a very nice topic of combination of language science and data science, okay, linguistics and probability. So probabilistic parsing is one of the nice examples of how linguistics and probability interact. Now, if we are thinking about the relevance of this discussion, then we should note that if all parsing after rule-based generation is probabilistic. Okay, and even today's LLM-based parsing, which is based on neural networks, they are also based on probabilistic parsing. And if the question is what is the linkage between neural networks and probability, the linkage is in terms of the softmax function, okay, which we'll have to discuss here, though this is a more relevant topic, in fact, the foundation for the next course, which is CS772, Deep Learning for Neural Network. So this is the line of development. Neural networks can compute probability through the softmax function, and probability is obtained from data. Data is annotated with parse information, the tree structure, and the trees are converted into linear bracketed level sequence, and these are trained on machine learning model. Okay, so this is the probabilistic parsing development. And we would also like to delve into dependency parsing today. So let's proceed. So as usual, we do a recap of what happened in the last week. A number of very important fundamentals were covered there. Okay, the first point is that when we have constituency parsing, then we would like to know what is the meaning of the parent-child relationship. In any tree, there is parent, and then there are. Can you stop talking at the back? Can you stop talking? So there are parent and children. Now, if a parent has a number of children, then the meaning of the parent-child relationship is that the children form the parent. Okay, so the combination of children that gives rise to the parent. So a number of small phrases coming adjacent to each other form the phrase. Okay, so for example, with a blue ball, a blue ball is noun phrase. With an a blue ball, which is a noun phrase. So preposition plus noun phrase gives rise to preposition phrase. So this is how the larger phrases are composed, and the children are used to form the large phrase. That is the meaning of parent-child relationship. But there is another relationship, which is the sibling relationship. Okay, if two entities are children of the same parent, then is there a relationship between them? The answer is yes. So if there are many children of a parent, then one of them is the head, and others are modifiers. So if you take this example here with a telescope, which is the preposition phrase, then the preposition phrase has two constituents, P and NP. P is a noun phrase, P is a preposition, and NP is the noun phrase. So this means that for this preposition phrase, with is the head. For a preposition phrase, preposition has to be the head, and NP, determiner N, is the modifier for the preposition. Modifier in the sense of supplying the demand of a preposition. A preposition needs a noun phrase. So that is the modifier. Okay. So we understand the meaning of parent-child relationship and also the meaning of sibling relationship. These are absolutely basic concepts. So make sure that you understand them carefully. Okay. And also the probabilistic modeling would like to ask which node is the head with high probability, and which is the modifier again with high probability. And if the head modifier has been found out, that pair has been found out, what is the relationship between them? Is it a direct object, or is it the subject, or is it the instrument? Again, with probabilistic ranking amongst them. Okay. So everywhere there is a basic concept, and that basic concept is ranked or scored with probability. Okay. In machine learning, one of the main purposes of probability is scoring. Does probability have any other role than scoring? That's an important question. So do you know the answer? Is probability used for anything other than scoring amongst the multiple possibilities or hypotheses? Okay, so do spend some thinking on this. Now, we also had this interesting concept of pre-modifier and post-modifier. So English has both pre-modifier and post-modifier. In the example on the screen itself, with a telescope, for a telescope is post-modifier for with. It is coming after the preposition. Whereas for a telescope, A is the determiner, and that A modifies telescope. This is a pre-modifier. It is coming before telescope. Okay, so pre-modifier, post-modifier, both are there. Then in DP, dependency parsing, the head modifier relationship is expressed directly. Okay, it is indirect in case of constituency parsing. We say that the siblings are such that one is a modifier, one is a head, and others are modifier. But in case of dependency parsing, that expression is explicit. Also, that relation is given a label. For example, you can see here, a telescope, A has a modifier relationship with telescope. And telescope and with has an object relationship. This is explicitly labeled. Okay? So while we are discussing all this, you should continuously, in your mind, think of the situation as one of classification. Okay, we are continuously deciding which node is the modifier, which is the head, and amongst head and between head and modifier, what is the relation? Okay, so it is also a classification problem. Then we also have seen that syntactic tree helps in disambiguation. For example, by proximity relationship. So you recall the example of I saw the boy with a telescope. Who has the telescope? Is it I or boy? So if the attachment is with saw, if the preposition phrase is closer to saw in the parse tree, then I have the telescope. If the preposition phrase with the telescope is closer to boy, then the boy has the telescope, right? So there is a proximity relationship. It's also called Sannidhi in Indian linguistics. And Sannidhi is not a trivial concern. Okay, Sannidhi is a very, very important concern. If you have been carefully observing how we process sequence, how is sequence processed, then everywhere we make Markov independence assumption. And the Markov window of k words, all these k words are adjacent to each other within a window of size k. And that adjacency is Sannidhi. Okay, Sannidhi is proximity. Then we have also discussed very important algorithm, and these algorithms took a long time to develop. And if not NLP, other branches of computer science have benefited from them. For example, for top-down parsing, TD, compilers have used them for parsing programs. And this is called recursive descent parsing in compilers and programming languages. In bottom-up parsing, we continuously look at the words and resolve the part of speech, combine parts of speech to phrases, and adjacent phrases to longer phrases. Bottom-up parsing is called LA-LR parsing in compilers and programming languages, or LR1 parsing, for example. Okay, so this is bottom-up parsing. Top-down bottom-up parsing is called chart parsing, very elegant. You have continuous alternation between top-down and bottom-up processing, right? So this is TD BU parsing. Sorry, CYK parsing is most elegant, And this algorithm has remained the cornerstone for all generations of parsing. Rule-based, statistical, neural, everywhere. Actually, CYK parsing is the bottom line idea. Then came a very interesting concept, the concept of domination. Okay, and domination is also called yield in compilers and programming languages. After my yesterday's lecture, some student I think was talking to me and said that natural language has copied these ideas from programming languages and compilers. Not that it is exactly the opposite. Okay, compilers and programming languages have borrowed these ideas from natural language processing because context-free grammar was the starting point, and context-free grammar came from a very celebrated linguist called Chomsky, Noam Chomsky from MIT. So the notion of domination got the term yield or coverage in programming languages. So here is the notion: XP:(Q) means the phrase or part of speech X dominates or generates the text segment from position P to position Q. For a word, P and Q have a difference of 1. Okay, so if there is a word from position number 3 to position number 4, remember that these indices are always between words, not on the word, between words. For between words, it is a very useful device to have indices which facilitate parsing. Then the probability of a context-free grammar rule. This links linguistics with probability. Okay, the probability of A goes to BC. Let's say NP goes to adjective phrase and NP. So noun phrase is composed of multiple adjectives and a noun phrase. So A is NP, arrow at JJP, which is B, C is NP. This means it is the conditional probability of a joint probability. Probability of B and C given A. So what is the probability that the non-terminal A generates B and C? Okay, and B and C in turn get developed to produce segments of text on the sentence. Okay, a whole territory of the sentence, a whole segment of the sentence is under the control of a phrase. Okay, the whole sentence is dominated by S. S is the supreme commander that dominates the whole sentence. And in that sentence, the noun phrase part is commanded by the symbol NP. Rest of the sentence, which is a VP, is commanded by the symbol VP. The verb phrase is commanded by the symbol VP. Okay, and then within VP, you can have variations: a single verb and a long noun phrase, or a single verb, a noun phrase, and another noun phrase, and so on. Preposition phrase, and so on. So what is the probability that this part of the sentence is dominated by a noun phrase and not verb phrase, let's say? Okay, that is the probabilistic question. And a very important a very important set of independence assumptions is independence of position, context, and ancestry. Independence of position is also called stationarity. The rule and the probability of that rule, the probability of a rule is independent of its position. Wherever the rule is applied, the probability remains the same. Okay, is there an exception to this rule? Think about this. Will the probability change? NP goes to DTN with 60% probability. Will this be the case anywhere in the sentence? Okay, think about this. This is a tricky question. So independence of position, context, and ancestry. The siblings don't affect the probability. Probability of NP going to DT NP is not affected by who the neighbors are. Is there a verb phrase around it or an adjective phrase around it? Doesn't matter. The probability remains the same. And also, it is independent of the ancestor path. Okay, from a node, there is a path going up to S. None of these nodes in the path affects that probability. Okay, so there are equivalent independence assumptions for hidden Markov model. Okay, the independence of position, which is called stationarity, and also Markov independence assumption. There is no ancestry assumption. Okay, so this a number of very important foundations for NLP were covered. NLP and linguistics were covered last week. If you had any question, I'd be happy to answer. Question, comment. Yeah. Hmm. Yeah. For parsing or parsing? Parsing. No. Ancestry is there. No, everything, everything. So so the probability of P going to it, the probability of P going to it, because P can go to, by probability, P can go to it by, into, inside, into anything. The probability of P going to with is, let's say, 20% amongst all the prepositions. So this probability is not affected by NP, which is its sibling. It is also not affected by its parent PP. And PP's parent could be NP. That also doesn't affect. And final parent is S. That also doesn't affect. Because you see, the probability of the tree is expressed as what? As a conditional probability. The whole tree is generated from S. Okay, this S should continue everywhere because the tree is a joint probability of all the nodes in the tree. This S should continue everywhere, but it gets stopped. The probability of this tree is probability of NP, VP, DT, NN, V, ADV. Also, okay, this is a joint probability given S. Okay. Now we have to break this probability into small parts by chain rule. So this will be probability of NP given S into probability of VP given NP and S into probability of DT given NP, VP, S, and so on. We will not do that, of course. What we will do is that we will say probability of NP and VP given S multiplied by probability of DT and N given NP, VP, and S. Okay, and so on. So we'll group them according to rules which are given to us. And in the conditioning part, everything will keep coming, keep accumulating because of the law of probability. And then you apply ancestry, ancestry will have to be applied because S will come. Okay, and also these nodes will come in the conditioning part. The ancestry will come, and then of course siblings also will have to be dropped. So ultimately, what will happen is that the probability of the tree will be the probability of these rule applications. S goes to NPVP has probability 1.0 if we have only declarative sentences. NP goes to DTNN maybe 0.6. VP goes to VADB maybe 0.4. So all these probability values will get multiplied. Anybody sees similarity between hidden Markov model and context-free grammar? Anybody? Any other answer? Yeah. Any other answer? Any other answer? How many of you have done theory of computation? All third yearites and also all master students. Theory of computation, right? So you probably know that regular grammars are special cases of context-free grammar. No? Right? Regular grammars are special cases of context-free grammar. So probabilistic regular grammars will be special cases of probabilistic context-free grammar. Probabilistic regular grammars are hidden Markov model. Okay, hidden Markov models are probabilistic finite state automatons, and finite state automatons can be expressed by regular grammar, and the probability associated with the finite state automaton, probabilistic finite state automaton, are associated with probabilistic regular grammar rule. Okay, so that's an interesting exercise. A good midsem question, I think, to think about this. The bridge between probabilistic context-free grammar and hidden Markov model. Okay, so this was done, and let's proceed. Okay, now we come back to the notion of domination, and the sentence is dominated by symbol S, and parts of sentences are dominated by phrases. Okay, for example, the gunman sprayed the building with bullets. Here, the gunman is dominated by a noun phrase, and sprayed the building with bullets is dominated by a verb phrase. Now, if it so happens that the domination of verb phrase over sprayed the building with bullets happens through three equally empowered assistants, that is through VBD, NP, and PP, who are at the same level, then the bullets are with the gunman. Let me repeat this point. If the domination of VP is affected by three subordinates of equal rank, that is VBD, NP, and PP, all at the same level, then VBD dominates sprayed, the building is dominated by NP, The indices are important, 3 to 5. And with bullets is a preposition phrase, dominated by a preposition phrase. So the structure of the domination here is such that the verb phrase has subdominations of equal rank through VBT, NP, and PP. If this is the case, then the bullets are with the gunman. If, on the other hand, the domination of the gunman is by NP, that doesn't change. The verb phrase dominates, sprayed the building with bullets, no problem. But the subdomination has a different structure. VBT dominates sprayed, but a large NP dominates the building with bullets. And that domination happens through two subdominators, NP and PP. And that shows with bullets is with attached to building, as if the building has bullets. Now, VP is dominated by two commanders of equal rank, VBT and NP, unlike the last parse tree, where VP's domination was affected by three commanders. Here it is affected by two commanders. Okay, and the meaning also has changed. The bullets are with the building. Okay, so this has a strange meaning though. What is the meaning of this sentence then? The gunman sprayed the building which has bullets. Sprayed with what? Okay, and also there are other complex natural language phenomena. There is a metaphor here. Do you see the metaphor? What is the metaphor? Spray. It is as if you are painting. Okay, that means that so many bullets are used that there is a cover of bullets on the wall of the building. That is the metaphor. Many complex NLP language phenomena are happening here. Okay, so the probabilistic parsing is, of course, started with argmax, and a very nice simplification happens where probability of S given T is 1 and gets dropped. So that possible tree, that tree is the answer which has the highest probability. Okay, the probability, that particular tree is output through parsing, which has the highest probability. So this is very intuitive. Now the whole business is to find out the probability of a tree, which gets done through the independence assumption. So we have the constituency parse here of I saw a boy with a telescope, where I have the telescope. The corresponding dependency tree is also shown. So the tree is the structure for both constituency and dependency. So in case of constituency, the root is S. In case of dependency, the root is the main verb. Everything else is linked to the main verb. Okay. And we know that this kind of parses give rise to data. The data is in the form of bracketed structures. Okay. Now, the second parse tree is also here, where I saw a boy with a telescope. The boy has the telescope. And you see the dependency tree also is accordingly different. A boy, fine, one modifier. The other modifier for the boy is with a telescope. How do I know with a telescope is a modifier for the boy? That is because PP is sibling to N, which is boy. So here the boy has both pre-modifier and post-modifier. And the bracketed structure, which is the data for training a machine learning model, is different. Fine. Formal definition we had seen. This is exactly same as context-free grammar, but the additional entity here is every rule also has a probability. Okay, and the meaning of rules is that probability of NP goes to DT is 0.2. Probability of NP goes to NNS is 0.5. NP goes to NPPP is 0.3. So the probability values have to add to 1 because NP has to be one of these substructures. Now here comes the rules. We note the rules here. S goes to NPVP is 1.0. It is 1.0 because we are concentrating only on declarative sentences. Our world consists of declarative sentences. So if the grammar had to accommodate imperative sentences, which are requests and orders, and also questions, then of course S goes to NP VP will not be the right rule. It will be NP goes to VP. Okay, VP, and then VP will get developed where NP is empty. NP goes to DTNN is 0.5, NP goes to NNS is 0.3, NP goes to NPPP is 0.2. PP goes to PNP is 1.0. Preposition phrase must be composed of preposition and noun phrase. So that probability has to be 1.0. There is no uncertainty there. VP, verb phrase goes to VP and PP, 0.6. So 60% probability that a verb phrase is composed of verb phrase and preposition phrase, 0.4 for VBD NP. So we get these numbers from the data, okay, from the annotated data. That is the importance of high quality annotated data. And the more difficult or more complex an NLP task, more important it is to have very high quality annotation. So while all this discussion is going on, I am sure you have a question in your mind that in today's NLP, we see the use of LLMs mainly. And LLMs have large number of parameters, huge amount of data. Who will sit down and annotate data for parsing? Millions and billions of sentences. Who will sit down and create data for parsing? Then how come LLMs do so well in parsing? Have you wondered for this question? It is impossible to create annotated data for trillions of tokens, billions of sentences. You do not have that kind of money, time, and expertise. And how come? What happens? What is the mystery? Self-annotate, no. Any other answer? Close. So this is affected through fine-tuning. Okay, you have an extremely large language model, huge amount of context. The conditioning part is very, very long. You predict the probability of the next word. Okay, in that process, the parameters in the model get trained to predict the next word. And then you take this model and take a reasonable amount of amount of annotated corpus, which is parse tree. So parse tree is available as some data, and fine tune the model with that data. That delivers the result. Now the question is, what has the prediction of next word, okay, or next language object, got to do with parsing? Is parsing also a prediction problem? Parsing is a prediction problem. Predict the next bracket, predict the next level. Okay, what has this got to do with prediction of the next language object? What is the relation? Okay, so I typically answer this question with an analogy. That is not a fully satisfactory answer. So suppose you are a sportsman who play cricket, football, volleyball, badminton, anything. Now, don't we know that if we do stretching, cardio, jogging, running, weightlifting, the body gets tuned, stamina gets built, and now I can play any sports. Okay, so the prediction of next language object is like this kind of stretching and training for the machine learning model. And then the task for which the fine tuning is done is the specialized training done for volleyball, cricket, football, badminton, anything. Okay, so that is the analogy. So you will say that this is not a very scientific answer. So now investigate in this line as to why the parameters which are trained for predicting the next language object with a small amount of task-specific data produces the result for that task. Okay, is the question clear? Think about this. Again, the answer lies in the law of probability. Law of probability, which is marginalization. So I can introduce any random variable through marginalization. In the probability expression, I can introduce any new random variable through marginalization. Okay, and when I introduce this, all this is very loose. Okay, not completely rigorous, but this is the way to think about it. The probability of parsing as a task, given the sentence, is marginalized over a language modeling task. Okay, where LM as a language model random variable takes all possible values. Okay, and then there are independence assumptions and further details, okay, which can go over the layers of the neural network and show that, yeah, a large language model which is trained for predicting the next language object well will also have reasonable performance, probabilistically speaking, on the parsing task or sentiment analysis task or machine translation task, any of them. Okay, so the law of probability allows us this kind of framework and thinking. Okay, now we can look at the probability of the tree. The gunman sprayed the building with bullets. It has two parse trees. One is when the bullets are with the gunman. So for that, the probability of the tree is the following. Probability of the tree is 1.0, which is S 1.0. S goes to NPVP has probability 1.0. And then NP goes to DTNN has probability of 0.5. That's why 1.0 into 0.5. Into 1.0, which is DT going to the into 0.5, which is NN going to gunman. So this you can see is a depth first traversal of the tree. Okay, so we keep collecting the probability values from the nodes in a depth first manner. And when we take the product of these probability values, we get the product as 0.00225. The probability of this tree is 0.00225. But this sentence has another tree where the bullets are with the building. For that, again, I compute the probability of the tree, which is 1.0 into 0.5 into 1.0 into 0.5. That is the NP part of the tree. Now, again, I am taking the product. I should not have done this because I've done this for the previous tree. I should just take the product and plug it here. Okay, so that would be dynamic programming. And the probability of this tree comes out to be 0.0015. The probability of the previous tree is 0.00225. So since this tree has higher probability, we'll output the parse tree to be this tree and not the other tree. And it so happens that we have produced a tree which is semantically viable. It is the gunman who has the bullets. Why should the building have bullets? I mean, that has a very strange meaning. And the probability also comes out to be higher for the semantically viable tree. Will it be always the case? No. Okay. It depends on the data. The parser has no idea of the meaning of a gunman, the close association between gunman and bullet, the fact that building with bullets makes no sense. All these nuances the parser doesn't have. It is completely determined by what the data tells it. So data has assigned the probability value such that this tree has higher probability value than the other tree. And the probability values are associated with the rules. The rules that are applied, their product is taken. So we have been able to get the probability of the tree which is semantically viable as the correct tree. Okay. And if the rules are such that we always have semantically viable tree as the winner tree, then we say that there is syntactic semantic consistency for the parser. Okay. All right. So any questions so far? The fact that we compute the probability of a tree by the product of rules is the basic operation. This has to be done efficiently so that you don't recompute the probabilities of parts of the tree, okay? Which is Viterbi-like situation. We will be able to kill the probabilities, we'll be able to kill the subtrees which are being formed because their probability is less compared to the other trees which are dominated by the same non-terminal. Same non-terminal means same state, like Viterbi. Same non-terminal means same state. Okay. So just like you kill the paths which are ending in the same state but have low probability value, here also you kill those subtrees from further development. You don't have to develop these subtrees anymore to have their subtrees because these subtrees have lower probability value compared to other subtrees for the same non-terminal. So the var phrase, which is showing that the bullets are with the building, if that subtree has lower value, then this subtree will be eliminated from any further process. Okay, so we'll have to look at the algorithm for. So there is some very important mathematical machinery which we need. Okay, for example, in machine translation, we'll need expectation maximization. So let's do a bit of these mathematical tools. And this is an important concept for us. Otherwise, this was always going to the bottom of the stack. Okay, I thought I should do it at some point of time. Expectation maximization. So the basic for this is maximum likelihood of the observation. Okay. So we know that when we throw a single coin, what is the probability of head that we can compute as a ratio of counts. If there are k heads out of n throws, then we say that k by n is the probability of head. The question is why? Okay, I don't know if any of you asked this question so far. If 100 times a coin is thrown 100 times and 60 times the head appears, then the probability of the head is given as 60 by 100, which is 0.6. Why so? What is the basis for this this computation? Okay, the reason is this. We apply a principle called maximum likelihood. Okay? And maximum likelihood happens to be the one of the most important principles in whole of machine learning. Okay, there are other competing optimization functions. Let's say maximizing the entropy. Okay. And there are others, but these two are most famous. Maximum entropy, maximizing the entropy, and maximizing the likelihood. So we want to find out the parameters, the probability of head, which we call P, for a single toss. Okay. Let n be the number of tosses. Now, the probability of head is found by maximizing the likelihood of observation. So if we have found that k heads have appeared out of n throws, then we have to maximize the probability of this observation. So if the question is the observation has already happened, what is the meaning of maximizing this? Well, the observation has appeared amongst many possibilities. Okay, if I have thrown a coin n times, then what is the total possibilities of sequences? How many sequences are possible? 2 to the power n. Okay, so out of 2 to the power n, in front of me, I see k heads have appeared. So this could not have happened. Okay, some other sequence might have appeared. So this is controlled by what? A parameter, and that parameter is the probability of head. Probability of head as a parameter controls this appearance of the observation which is in front of me. So I want to investigate further and find out what could be this probability P. What could be the value of this parameter, which amongst all possibilities has produced k head, 60 heads out of 100. It could have produced 1, could have produced 100, could have produced 35, 36. Why not any of them, but 60 heads out of 100? Why? Okay, so the reason must be in some controlling parameter, which is controlling this experiment. Okay, so then let n be the number of tosses, then the observation x and the data or observation likelihood d respectively are the following. X is a sequence of indicator variables. They are also random variables. They take value 1 or 0. So if x1 is 1, then first time I toss the coin, I get head. If x2 is 0, then it is tail. x3 is 1, head, and so on. So I can represent the sequence of heads and tails by ones and zeros. Okay. So the data, or the probability of the whole data is equal to I equal to 1 to n, p to the power xi into 1 minus p to the power 1 minus xi. Okay, so maybe you can see it more directly in the following way. Indicator variable actually facilitates the mathematical operations. So without indicator variable, if p is the probability of head, then what will be the probability of this observation under IID? Okay, what is IID? Identically independently distributed. Okay, so the probability of the phenomenon happening at any position is independent of any other position, right? So if you have got k heads out of these n tosses, then the probability of the whole observation, is the product of individual observation. Product of the probability of individual observation under IID assumption. So head has appeared k times. So p to the power k P into P into P, K times is the probability of obtaining head. And 1 minus P to the power N minus K is the probability of obtaining N minus K tails. So at every location, I have the probability of the observation. I simply take the product of those probabilities. So the data probability or the observation probability is P to the power K into 1 minus P to the power N minus K. This is exactly equivalent to the expression with indicator variable. Okay, convince yourself that this expression P to the power K 1 minus P to the power N minus K is equivalent to this expression. Okay, so let us do some board work. D is K heads and N minus K tails. So observation probability of D is equal to P to the power K into 1 minus P to the power N minus K. Okay. So I have to maximize the probability of the observation by choosing P appropriately. P has the value between 0 and 1. Right. So now I'll work with log PD, that is log probability, which is equal to, let me use the correct notation as you see in literature. So likelihood L is P to the power K into 1 minus P to the power N minus K. So log likelihood LL is equal to log P plus N minus K into log 1 minus P. Right? Log likelihood of the data is K log P plus N minus K into log 1 minus P. N is constant, number of throws. K is constant. K has already happened. So many head. Don't know P. P is variable. So to maximize the log likelihood, I take derivative of log likelihood with respect to P. Is it visible from the back? The board is visible from the back? DLL dP is equal to K by P plus N minus K by 1 minus P into minus 1. Okay, do a very simple problem. This is exactly the set of steps which are used for maximizing likelihood, whatever be the problem. You first have to set up the probability of the observation. Typically, you have to take log likelihood. And typically, you have to differentiate with respect to the parameters. If there are multiple parameters, then partial derivative. Typical operations, whatever be the problem, single coin or an extremely complex process control problem. Okay, or a modeling of the election phenomena, weather prediction phenomena, everywhere, same principle. Okay. So now maybe some of you know the underlying reason why the probability of head is k by n. N is the number of tosses, k is the number of heads obtained. Coming from the observation, from the data, nothing else, coming purely from data. Okay. And it can be shown that uh, under the constraints, okay, with the available information, you cannot have a better estimate for P. Okay, do whatever you want. You take maximizing the entropy, maximize, do Gibbs sampling, do anything. This is the best possible estimate for P. So another probability, right? The probability of head is maximized here. Okay, the best possible estimate of the parameter P is k by n. You cannot do better with the data that is available. Okay, so now I think for some of you at least, it is clear why we take that ratio. And whenever you see a ratio, you must understand that a maximum likelihood estimate principle is in operation there. The underlying operation is maximum likelihood. What is the probability of a noun following an adjective? 0.8. How do you know? I have counted the number of times the noun appears after adjective, and I have also counted the number of times the adjective appears in the corpus, taken the ratio, and this is the estimate. Why? Why? Because maximum likelihood estimate principle. What are you maximizing? What are you maximizing? What are you maximizing again? Probability of the corpus. So if you have got a billion token corpus, the probability of that corpus. Okay, and given the whole corpus, the probability of noun given the adjective is 0.8. This can be obtained from indicator variable. So that's why the notion of indicator variable is introduced here. Okay, there's an indicator variable whose value is 1 if a noun comes after adjective, otherwise it is 0. And umpteen number of interesting things can be done with the indicator variable. If you're not used to indicator variable, get used to it. This is one of the important tools for machine learning. Indicator variables are very attractive. First of all, they take value 1 or 0. And their expectation is probability. Expectation of an indicator variable is the probability of the indicator variable being 1. Very attractive. Okay. So the reason for probability being k by n is now known. Okay, let's see it through the through the lens of indicator variable. So this is the data probability. Data probability is product I equal to 1 to n p to the power xi 1 minus p to the power 1 minus xi. Xi takes the value 1 for head, else 0. And these two expressions are equivalent. You should convince yourself these two expressions are equivalent. So for single coin, then since exponents are difficult to manipulate mathematically, we take the log of d, also called log likelihood of data, and maximize with regard to p. This yields, that is, this expression is interesting. P comes out to be equal to I equal to 1 to n xi divided by n, and I equal to 1 to n xi, sum of indicator variable. Do you remember? Sum of indicator variables is equal to count. Xi takes value 1 or 0. Okay, so since xi is 1 when the position gets ahead, okay, the toss is tilting ahead, this is exactly equal to number of heads, but expressed through indicator variable. Okay, so k equal to I equal to 1 to n sigma xi. Okay, here I'm using m and n. Now we introduce expectation maximization. through another very simple example of two coins. Okay, expectation maximization is typically taught through mixture of Gaussians. That's also a nice way of teaching, but I think this is better. Okay, it is in the discrete domain and teaches EM through, again, a very simple situation of tossing of two coins. So look at this. When you toss two coins, there are three parameters. The probability is P1 and P2 of heads of the two coins. First coin P1, second coin P2. And the probability P of choosing the first coin. Automatically 1 minus P is the probability of choosing the second coin. Okay, the setting is clear. Now there are n tosses and there are observations of heads and tails. Only we do not know which observation comes from which coin. We have to estimate the value, best possible estimate of P1 and P2. The probability of head from coin 1, probability of head from coin 2. So this is very difficult if we do not introduce the concept of indicator variable. Okay, so the indicator variable Zi is introduced to capture the coin choice. Zi equal to 1 if coin number 1 is chosen, otherwise this is 0. This variable is hidden, that is, we do not know its value. Okay, nobody tells us from which coin the observation has come. We choose a coin randomly and throw it. However, without the likelihood expression would have been very cumbersome. Let us see. So with the help of Zi and the two indicator variables corresponding to two coins, we can formulate the data likelihood as follows. So data likelihood is probability P1, P2, P3. P1, P2, P3 are in the suffix. They control the probability of X. X is the observation. So P theta X, where theta is P, P1, P2, is sigma Z, PZ, X, comma, Z. So we are interested in P theta X. That is the likelihood of data. Okay, P theta X is the likelihood of the data. This expression. This is what we are interested in. And we have introduced an indicator variable Z. So this Z can be introduced by marginalization. All possible values of Z, which is sigma Z, P theta X, comma Z. Z takes two values. So X is X1, X2, X3 up to Xn. And in parallel, we have the indicator variable of which coin is chosen running in parallel to this. We have Z1, Z2, Z3 up to Zn. So if, let's say, Z2 is 0 and X2 is 1, Z2 is 0, X2 is 1. What does that mean? What is that? Coin 2 was chosen and the tail has been obtained. Okay, so probability will be corresponding to the phenomenon or probability of choosing the second coin and probability of obtaining the head from the second coin. So P theta X comma Z can be written elegantly as I equal to 1 to n. I runs over the whole observation, 1 to up to n. P1 x to the power I, 1 minus P1 to the power 1 minus xi, to the power Zi, okay, multiplied by 1 minus P2 to the power xi, 1 minus P2 to the power 1 minus xi, to the power 1 minus Zi. So notice that if Zi is equal to 1, then the second part of the expression, 1 minus P, P2, etc., vanishes because index is exponent is 0. So if Zi is equal to 1, then everything is with respect to the first coin. Okay, and that's why we have P1 to the power xi, 1 minus P1 to the power 1 minus xy, just like the single coin, except that this is multiplied by a P because this is a joint probability and independent. We have chosen the first coin and the probability of head coming from it, probability of tail coming from it, just like a single coin. And if Zi is 0, then the first part of the expression disappears. Okay, this part disappears. And the second part gives me 1 minus p into p2 to the power xi, 1 minus p2, 1 minus xi, just like a single coin. Except that the whole thing is multiplied by 1 minus p, because, like for joint probability. Second coin is chosen, and rest of the consideration is for head and tail. So this expression is making sense with respect to which coin is chosen and what is happening to the observation. Okay, you can also derive this rigorously from the rules of probability. Okay, now so our goal is to maximize p theta x. And in that process, we would like to work with log p theta x. However, there will be a sigma inside log. Because you see, we have log sigma z p theta x comma z. So log p theta x will go to log sigma z p theta x comma z. Now, here what is applied is the theory of convexity. Fortunately, log is a concave function, so that log of I equal to 1 to k, lambda I yi is greater than or equal to sigma I equal to 1 to k, lambda I log yi, with sigma lambda I equal to 1 to k equal to 1. What is happening? All that is happening is that the sigma inside the log is inconvenient to process, so get the sigma out by applying convexity. This is the top level picture. Okay, but detail will work out later. So this is because of concavity. Now, log likelihood of the data is log of p theta x, which is log of sigma z p theta x comma z. And this can be written as sigma z lambda z log p theta x comma z divided by lambda z. Okay, there is a series of mathematical operations which is involved with it. The outcome of all this is that the log likelihood of the data comes out to be lower bounded by an expectation over log of p theta x comma z. Okay, the summation disappears, bringing in expectation of z given the observation x and the parameter theta. And we have log of p theta x comma z. Summation and probability, you know, is a way towards expectation. If you have summation and you have probability, then you know that from here I can move towards an expectation expression. So the log likelihood of the data is lower bounded by an expectation of log p theta x comma z. Now log p theta x comma z is quite good in terms of its operations. So p theta x comma z has this expression, which is the product. Okay, this product, and we operate log on this. So z I comes down and produces log p plus xi log p1 plus 1 minus xi log 1 minus p1. Just application of log plus 1 minus zi log 1 minus p plus xi log p2 plus 1 minus xi log 1 minus p2. Okay, so expectation of so I equal to 1 to n, expectation of zi xi given xi, and log of p plus xi log p1 plus 1 minus xi log 1 minus p1 plus 1 minus E zi given xi log 1 minus p xi log p2 plus 1 minus xi log 1 minus p2. What is applied here? The linearity of expectation. Expectation of x plus y is expectation of x plus expectation of y. Okay, so expectation is distributing over the two terms such that zi xi equal to 1 or 0 and p, p1, p2 are all probability values between 0 and 1. Okay, so we'll continue with these expressions. Okay, you will see that every step follows from the previous step very systematically. Okay, there is no surprise anywhere. But you see I would like to show you the final expression. See this expression carefully. The probability P of picking up the first coin comes out to be equal to expectation of zi under the data xi. And this expectation zi under xi, I equal to 1 to n, is nothing but the expected count of the times the first coin is chosen and divided by n. P1, which is the probability of obtaining head, is nothing but the number of times the first coin is chosen. This is in the denominator. And out of the number of times the first coin is chosen, how many times head appear? The expected count. So all the counts are now in terms of expected counts. Similarly, P2. So this we'll look at in little more detail, very instructive. And expectation maximization will be required for many things in anything. Okay, so we'll stop here. Just one or two announcements. One is that we had your assignment evaluation on Saturday. Okay, and I'm happy to see that the marks are quite good. A lot of above 40. Now you try the CRF-based implementation and compare with HMM. Also, the office hours for all the evaluation teams and myself has been publicized on Teams. I think my office hour is 3 to 4 o'clock on Tuesdays. Okay, so I'll be available tomorrow onward in my office 3 to 4 o'clock. Other TAs will be available in the Seafield lab in the given times. Okay, just clear your doubt.